Take a look at the Coulomb's law page. I believe this is page 6 in your packet. Alright, so we just learned that last class that the equation for Coulomb's law is this. And it looks at first like it's a really challenging equation, but it's not too bad. Remember that these Q's, they both stand for charge. Notice that they're the same as if we had Q equals NE. We're looking for overall charge. This would be like if I knew my overall charge for one charge, I knew my overall charge for a second charge, and then we had to look at some other things here. Hopefully you can look at this equation by now at this point in the year and be able to see pretty much what's going on, even if you've never seen the equation before. You could look at it and say, well, I know F is probably a force, right? E is, well, we're in the electrostatics unit, so probably talking about an electrostatic force, and it is. Force is going to be in newtons, and then we could continue to look at it and say, well, maybe I don't know what K is, but I do know that Q stood for charge in the other equation, so now I've got two charges, so it must be dealing with these two charges in relation to one another somehow. And then we look at the bottom, and it looks like, oh, well, D is most likely distant, so I can look at this equation overall and say, well, it looks like the electrostatic force is based on this K thing and then two charges next to each other a certain distance, and K is our constant. That is always going to be the same, thus constant, and it's always going to be 9 times 10 to the 9th. We're not going to really worry about the unit. It's long, it's convoluted. If you flip over to page 7, you can see it. But we're never actually going to be solving for K, so we're never going to have to really worry about that unit. What that unit is for, however, is to cancel out the N on forces, to cancel out the C's for coulombs, to cancel out the meters squared for our distance. And then it leaves us over with just the unit that K is. So each one of our Q's are in units of coulombs. All right, we know that from before. Distance is going to be in meters, and like I said, force is going to be in newtons. All right, so let's go ahead and take a look at how to use this formula. So first thing, before we even get into any of the problems, we got to know what's going on in relationship between F and the rest of this, and distance and the rest of our formula. Same with Q and the rest of the formula as well. We're not going to worry about K yet so much. What K is, like I said before, it is a constant, and it's meant to get us a value that makes into it a little bit more later. But what's the relationship between Fe and charge? It is direct, but you may be thinking, well, how do I, first of all, hopefully by this point in the semester, you could say, well, if I've got some sort of mathematical expression where I've got a numerator and a denominator, whatever's on this side is going to be, it will have a direct relationship to whatever's in the numerator on this side. If that doesn't make sense, do a couple of problems and allow a sort of experiment and allow for the formula to tell you essentially what the relationship is. So for example, I could set this up and say, well, F is equal to, kind of equal, Q2 over D squared. Let's just not worry about the constant right now. Alright, well, if I change, if I got to start somewhere, let's go ahead and throw in some 1s here for Q. Let's go throw in a random value of 1 for distance. The reason I'm using 1 across the board is just because it's a very easy number to multiply by, really easy number to square. I don't really have to use a calculator. So I would come out with, well, this equals 1. Alright, that makes sense. Let's go ahead and do this again. Let's increase the charge on one of my Q's. Let's now make it F is kind of equal to 1 times 2 over 1 squared. So I've just changed one of these values, increased it a little bit, and I'm experimenting to see what happens with F. Alright, well, in this case, my force becomes 1 times 2 is 2 over 1, still 2. So it looks like if I increase this Q, I also increase F. So that would be a direct relationship there. And you could keep going for a while just to make sure that, it's not just that you've done this one time and then been like, well, it might just randomly have happened that one time. Let's do it a few more times and see, is it in fact a direct relationship? It's not just a one-time occurrence. And I would do this again. 1 times 3 would be 3 over 1 is 3. So it looks like every single time I increase one of my Q's, I also increase F at the same rate. And that would be considered a direct relationship. All right? Let's go ahead and get rid of that. And take a look at the next relationship here. Alright, so what's the relationship between Fe and distance? So what's the relationship between the force and distance for an electrostatic occurrence? It is inverse square, and it's because if we look at this, the d is in the denominator, so that is, if this is in the numerator and this is in the denominator, the reason that I say this is in the numerator is because it could be the same as, let's go ahead and go back there, pick a smaller. The reason that I say that this is in the numerator is because we could say over 1. All right? And that doesn't change anything. It changes it a little bit conceptually, allows us to see it as a fraction, but in reality it doesn't actually change the value of f, because anything divided by 1 is going to be itself, including a variable. So this is going to be an inverse, since this is in the numerator and this is the denominator. But we also got to look, the denominator is squared. So that's where we get this inverse square from. And again, sort of like what I did up here before, we can look at the relationship between these two, between F and D, and see what happens. Again, let the math tell us if we kind of experiment around a little bit. So I'm going to do that in the same white space here. So we've got our formula. We're just going to say F is kind of equal to Q1, Q2 over D squared. And now, again, I'm playing around with D. So let's see what happens to F when I change D. Let's just go with some 1s across the board, because it's just really easy to go with those, with that number, because in the end we can just multiply things out, divide things out really easily in our head, do whatever else we need to with 1. So 1 times 1 is 1, over 1 squared is 1, 1 divided by 1 is still going to be 1. And that doesn't tell me anything, right? I have to do this a few more times before I actually see what's going on. So now let's come up with some other values. I'm not gonna touch Q. I'm gonna leave that 1. The reason I'm leaving that 1 is because I'm looking for the relationship between force and distance right now. I'm not looking for the relationship between force and anything else, so let's not do anything to anything else. So my distance, let's go ahead and increase it. Let's go to 2. Alright, the reason I increase my distance is I'm experimenting. Well, what happens if I increase my distance? What's going to happen to F? 1 times 1 is 1, over 2 squared is 4. Oh, so it looks like it went down. Alright, maybe I might be able to realize now that it's a squared relationship, but you could do it again just to be sure. So again, let's not touch our Q's, because we're not looking for anything with Q. We're looking for force and distance. Let's increase our distance to 3 squared. So then end up with 1/9. So it looks like this is not a constant rate. If it were an inverse relationship, it would be every time I increase my distance, I would go down by the same rate that I increased that at. But I'm not going down by the same rate, because it's not going from 1 to 1/2 to 1/4. It's going from 1 to 1/4 to 1/9. So it looks like anything I do to this, it's actually squared in the denominator. So that's where I'm getting this inverse square relationship from. And that may take a couple of times of going through it. Use different numbers than mine. Experiment around with it until you really get comfortable with that concept, because it's important. Alright, so now let's get into some of the problems. There's a few different ways that I can do these problems. Alright, and I'll show you what that is. But we also went over this in class. So number 1, if one charge is doubled, the other charge is tripled, what happens to the force? So what I like to do in these problems is sort of make up some numbers and then take a look at what happens after I've done something to those numbers that the problem's telling me to do. All right, so here's an example of that. So how can I tell what happens to the force if I don't have any numbers to begin with? And that may be what's sort of confusing. So make up some numbers. Again, I like to choose 1 for all of my sort of made up numbers, so to speak, because it's really easy to multiply by 1. Could you do something else for these Q's? Absolutely. You could do 1.89 and 2.342 and, you know, all over 9.89, but that's like really ridiculously random. It still could be done, and you just have to end up using your calculator to come up with what all these other values are, divide the two to see how much the force increases by, and you would still get the same answer as me. It would just be a little bit more convoluted. So let's take a look at this. All right, I'm going to come up with a charge of 1 Coulomb for each of my Q's, 1 meter for my distance. 1 over 1 is going to be 1. All right. So this number right here tells me absolutely nothing, because remember, it's made up. And this other number here, when I solve for it, is also going to tell me absolutely nothing. But it's the relationship between the two that we care about. So let's take a look at the second part here. So the reason that I can make up these, as long as I'm doing whatever the problem is telling me to do to these numbers, I'm in okay shape. So one charge is doubled. That's where I'm getting this from. I'm doubling my first charge that I picked. If I picked 2 here, then this would be 4. If I picked 3 here, then this would be double what 3 is, 6. Right? The other charge is tripled. So other charge being tripled, I'm going from 1 to 3 here. What happens to the force? Well, it didn't tell me to do anything to the distance, so I'm assuming I'm not touching the distance. I'm leaving it as is. Let's go ahead and solve out. This 2 times 3 is 6 over 1 squared is still 6. So again, this number right here also doesn't tell me anything. It's just coincidence that these two numbers are the same in this case. It tells me the relationship between the two. And it tells me something. When we talk about relationship between the two, we're always talking about how many times greater, how many times less it is. It's not that it's 5. This is 5 points bigger or 5 units bigger than here. It's that going from this side to this side is 6 times the increase. Okay. The reason that is also because if I use different numbers here, which would cause these to be different numbers over here, I could have something that's all along the lines of, I'm going from 2 to 12 or something like that. And then if a person ended up coming out with these numbers from whatever numbers they chose here, then they'd say, whoa, it increased by 10. Yeah, that's true, and it would be true that, you know, yours increased by 5, but they wouldn't be true in the sense that they're the same. So going from 1 to 6 is an increase of 6 times. Going from 2 to 12 is also an increase of 6 times. So that's why we always go with the factor that it increases by, or how many times it increases or decreases by. All right, let's go ahead and take a look at number 2 here. So if the charges are not changed but the distance of separation is tripled, what happens to the force? So I'm doing something very similar to what I did in the previous problem. The only difference is I am now dealing with my distance instead of my charge. So again, I sort of make up my numbers in the before scenario and then take a look at what happens in the after scenario. So go with all ones, makes your life a lot easier, but we could use something different entirely if we wanted to. So I know that I am not doing anything in my charge. It says charges are not changed. So from this side to this side, we're not changing them. If I did 2 and 2 here, it would be 2 and 2 over there. Also, I don't have to pick the same numbers for both these charges. I could pick 2 and 10. I would just have to make sure that I leave these as 2 and 10 then. Alright, distance of separation is tripled. So my distance, I'm going to end up tripling. So going from 1 to 3. I'm not doing anything with the exponent because the exponent's part of the formula. Alright, so I end up with 1 times 1 on this side over 1 squared is all 1. Again, this doesn't tell me anything. until I look at the rest of the problem. 1 times 1 on this side is 1 over 3 squared is 9, so 1/9. And this doesn't tell me anything, but it's a relationship between these two that tells me something. So there's a couple ways I could state this. I could say the force is reduced by 9 times, because going from here to here, and if you're having a hard time ever in terms of, do I say increase or decrease, always draw your arrow from the left side to the right side. Say, well, is this an increase or a decrease? Well, this is definitely a decrease. And then look at the two numbers. Always take your largest number divided by the smallest number, and that'll give you how many times an increase, or in this case a decrease, it is. So 1 divided by 1/9 is going to be 9 times. So the force is reduced by 9 times, or you could say the force decreases by 9 times, or the new force is 1/9 that of the original force. A bunch of different ways that you could say the same thing. All right, number 3, if the charges are not changed, but the distance of separation is reduced to 1/3 the original distance, what happens to the force? So you can see I'm picking 1 for my charges, and I'm keeping it the same. The only reason in this problem that I chose to change my distance originally to 3 is because it says it's reduced to, the distance of separation is reduced to 1/3 the original distance. It's really easy to take 3 and cut it into 1/3, right? Go from 3 to 1. But you absolutely could stick with 1 on this side, and then over on this side make it 1/3, and that would be fine as well. So again, we could look at this and say, well, from this side to this side, draw my arrow in. Is this an increase or a decrease? It's definitely an increase. And then let's take always the largest number divided by the smallest number and see what that increase or decrease is. In this case, the increase. 1 divided by 1/9 gives me 9 times. So we could say the force increases 9 times, or it increases by a factor of 9 would be another fine way of saying it. All right, take a look at number 4 here. If the charges are not changed, but the distance of separation is reduced to 1/5 the original distance, what happens to the force? In this case, I just picked some numbers other than 1 just to show that it is perfectly possible to pick other numbers other than 1, but you could absolutely go with 1, 1, 5, and then change it over here to 1, 1, and 1, because it's very easy to cut 5 into 1/5. You could go with 1s across the board, and then over on this side, change your distance to 1/5, and that's fine too. But again, I just kind of went with some random numbers here to show that it is possible to pick different numbers when you're sort of making these up, so to speak. So if the charges are not changed, but the distance of separation is reduced to 1/5, well, my charges not being changed, in this case, my original charge here, for some reason, I picked 2. I didn't change that charge over there, right? So that's part of my charges not being changed. And then my other charge that I picked was 3. So I need to make sure that, according to the problem, tells me not to change it. So I didn't change it here. So those stayed the same. It tells me that my distance of separation is reduced to 1/5 the original distance. For some reason, I randomly picked 20. So what's 1/5 of 20? Well, 1/5 of 20, 20 divided by 5 would be another way of doing that, is 4. So again, as long as I'm going along with what the problem's telling me to do, pick some random numbers, pick whatever numbers you want, but then just make sure that you're doing whatever the problem tells you to do to those numbers. All right, so when I solve it out, I get 6/400ths on this side. Again, that doesn't tell me absolutely anything. Then when I do the same thing over here, end up doing my math, I end up with 6/16. Well, that doesn't tell me anything at all either. Again, it's always a relationship between the two that tell me something. So it looks like this number is much smaller, so going from this side to this side is an increase. And then I would always, again, take the largest number divided by the smallest number. So 6/16 divided by 6/400ths ends up giving me 25. So the force going from here to here increases by 25 times. All right, let's take a look at Number 5 and 6 here real quick, and we'll be done with this page. So if both charges are doubled, the distance of separation is tripled. What happens to the force? Alright, so in this case I can go back to my ones just like I could have done before here. It tells me that both charges are doubled. So whatever number I picked here and here, I need to double that over on this side. Doubled it up, doubled it up. Distance of separation is tripled. What happens to the force? So the distance of separation being tripled, it's going from 1 here to 3 here. Again, could have been 3 and 9, could have been a whole bunch of other things, going from 300 to 900. It doesn't matter what it is as long as we do what the problem's telling us to do. So it looks like going from here over to here, and this would be 4/9. It looks like it's a decrease. All right. So what is it a decrease by? I'll take the larger number, in this case 1, divided by 4/9. There's a couple different ways we could state that. 1 divided by 4/9 is going to give me 2.25. So the force is either reduced to 4/9 of the original force. Original force was 1, the new force is 4/9. Or we could say, after doing 1 divided by 4.9, which comes out to 2.25, we could say it decreases by 2.25 times, or we could say it decreases by a factor of 2.25. All of those are saying the same thing, just slightly worded different. Number 6, if one of the charges is doubled, the others remains unchanged, and the distance of separation is doubled, what happens to the force? Here I'm going to do it a slightly different way, just because some of you guys might have by this point picked up that there is a shorter way for sure, and that's what we're going to do here. But you could have done this just like this problem, just like all the other problems on the page, but here's a little bit of a shortcut, and you may want to use this on some of the other pages. So one of the charges is doubled. So in front of one of my charges, let's go ahead and double it. That's where this 2's coming in. The other, let me highlight that so we can see where it's come from. The other remains unchanged. So if the other one is remaining unchanged, I'm just going to leave it as is. Q, still Q over here. Remember, these 1s and 2s for Q1 and Q2 don't actually tell me anything mathematically. They're essentially just record keeping. So first charge, second charge, but nothing math. We wouldn't multiply by it or add by it or do anything else with it. Then it tells me the distance of separation is doubled. So then that means I'm taking this distance and I am doubling it over here, and that's where that 2's coming from. So then I could say, well, what happens here? There's 2 over 2, and we need to make sure that we're squaring it here because that's part of the formula. So 2 over 2 squared is 2 over 4. So we could say the force reduces by 2 times, or we could say the force is 1/2 the original force, because 2/4 reduced would be 1/2 the original force.